Hello everyone, and we're back with 10 things again, looking at some of the features that we have within the Robotics Discovery Hub. Obviously, you set up a project is a robot, and it goes through a pipeline. But one of the things that most robotic companies struggle with is getting just USDZ files and URDF files out, SDF files out of CAD model. So what we're going to do today is we're going to import a CAD model, and then we're going to get those USDZ files and URDF files out of the CAD model. So I've done it many times, as you can see here, but we're going to do it live so that everyone can see. This is a project that we're working on called Amber, and it's a POC to demonstrate all of the work that we've been up to here at 10 Things. So one of the interesting parts about this is all you need to know is what the robot's supposed to be doing, how many degrees of freedom it's actually supposed to have, and here I describe it. These are the degrees of freedom that I expect out of the robot, and because of this, when I launch this USDZ view, I will get now an understanding of what's in the robot. So here, this happens in code behind, also will show up on the screen, but I thought it was interesting just to maybe show this so you can see that the CAD is completely kind of described. The entire assembly, including its relationships, are all here, and it creates 156 parts of this particular robot. If you refresh the log output, you'll start to see as it's generating logs for this. But for right now, let's just get started. You can see here, this is the robot. There, I'm going to move the robot around so you can see this is kind of at the bottom of the robot, etc. And what we're doing is we're creating images for a generative model to kind of understand what are the important features of the robot. So this is the inside of the robot. And the reason why we're doing this is because there are some parts of the robot that are not intuitive for the generative model to understand. This is what we want to actually move, and here's the link, and here's the joint that we're actually really concerned about. So in that way, we're going to just kind of show the important features to the generative model. And you're asking, why are we doing this? What's the purpose of this? The purpose is to let the generative model figure out what's important inside or on the outside of the robot. So we kind of got enough, I think, enough of an understanding. And these are just pictures, and then there's a way to auto collect pictures. So I'm going to do that, capture video for analysis, or pictures from analysis, and it's going to create a bunch of pictures, and we're going to send this along with the description, along with the comprehensive part list, the relationships that we think should exist from just the CAD model itself, the assembly. We're going to send all that to a generative model. So this actually takes a while. So we're going to click on that, and I might pause the video, or we'll just have a conversation. So there we've looked at the structure. Good. And now we're going to suggest joints from that. So hopefully you can still hear and see me, because sometimes the video freezes when this happens. But all of this, and just wait. It's going to be a solid 5 minutes while we're going through all of this. Why we're doing all this, and maybe I'll backtrack onto the Discovery Hub while this is going, is we want to understand truly what the robot's capable of. So when we get that CAD model, we want all of its subsequent parts to be understood. We're going to look for documentation on the internet. We're really using a research agent behind all of this that's just going to get everything that it can get about the parts that we're using inside, inside this particular robot. So if you look here, there are parts. Here are motors. Well described what the motors are. These are from my actuator. And, there's case mounts, there's wheel bases, there's pan and tilt cameras, and, all these things. All of these things have associations with code and associations with documentation, along with things like, if you're trying to do planned maintenance, you need to know cycle time. So all of these things have that. And, I'm using this 8 megapixel camera. It has a description. It also has code behind that we can use. So we can take all of that and put it into an environment in which we're able to now test the code, critique our tests all in one place. So this is the start of this. In order to get here, we have to have that description of the robot. So we start a project, we ingest the mechanical designs, the URDF file if you already have it, the specifications if you also have that, and documentation. So if you have the documentation as well that's associated with your robot, then you can upload all of that here. Now, and you might have saw a GitHub repo as well. So here it's suggesting 22 joints. I know it's supposed to be 29, but that is this is a generative model, so it's looking and it sees the pan and tilt camera, the fingers, the thumb base, all of these different things. And I've looked at this robot enough, I can tell exactly what's missing, and we can add that manually. But for today, we really don't care. What we're going to do is just continue on. I could refine with feedback, so I can say that it's, let's see if I can define something that I see it's missing. Wrist jaw. It may struggle with like revolute joints that are not obvious because it's looking at the pictures on the outside, not what's on the inside. So there is this, there's a set of revolute joints that are just for the, I would say there are missing roll joints in the shoulder, left and right, and the wrist roll, left and right. And it's because looking at the picture, so it's seeing this like the little sliver of information there, and I can click on refine or feedback, and it will go off and refine if it finds something. I can also manually add joints. So you're going to see that the querying AI, that's going to take the same process as it did before, and it'll add joints if it finds them. Or if it struggles, then you can manually add those joint relationships by going to the actual prem and just selecting the two items in the prem and where the joint belongs. So it's similar to, if you did this inside of Isaac Sim, similar to doing it there. Similarly, you can do this in the USDZ view. So back to this while it's doing that. If you have a repository and you have a one-time use key, we can grab the entire repository of information you already have. We'll categorize that information. We'll put it into the structure that we need in order to give you back more control code and move you on to that robot control hub. Artifacts will start to develop themselves. So here's the OpenARM URDF file that already been created. There's more than just these kind of artifacts. There's and this is an example. This is not I created one giant big file just to demonstrate some of these things, but you would get specific artifacts back, like the folders where the meshes belong and all of those things. And this is an artifact store. So as we do more things, like say we decide we want to create control code, and we click on create control code, you'll start to see that fill itself up in here. Any findings that you come across will also be here. If there are mesh warnings, which sometimes they're overlapping meshes or things like that, or high poly meshes, things that we want to just notify ourselves about will all be here. So back at articulations, we'll start to see that log files will start to generate themselves as we start to do more. and it found one more joint. Well, that's great, but we want all the joints. But let's go ahead and click on apply. And I know we're supposed to be around 27, 28, so we could add these joints manually. So I now when I look here, I have a list of joints: head, pan, and tilt, elbow, finger, left shoulder roll. So it found the left shoulder roll, left wrist roll, right wrist roll, right shoulder. I don't know exactly, not sure what it didn't find. Maybe it's smarter than I am as far as what joints are which. So there we go. That's kind of the hardest part there. And so we clicked on suggest joints, and then the next thing we're going to do, slightly out of order, is we are going to set up the articulation route. So I'm going to say, what should be the articulation route? Well, it suggests a particular articulation route. It thinks that the torso back V12 should be the route, and it's right. And this is all coming from a generative model. This is not me suggesting anything. And then from here, there's we can merge parts into links. We can add rigid bodies to selection. We can create joints, fixed, revolute, prismatic, custom joints, by the way. But I'm going to say let's add rigid body to all links. And then I'm going to say add collision to all links. Whoops, we already did that once. Add collision to all links. And then finally add drives to all joints. Now, I can individually set joints, drives, but I'm just going to add them all this way, just to, we're obviously just demoing. So I would be a little bit more prescriptive if I was going to try to do that the right way. And then the final thing is I'm going to see if there's any all joints are referenced as we thought, and it found 2 issues. So it found 23 joints. It found 1 floating part, and that's kind of a must fix. Okay. So I'm going to fix the floating part. Okay. And now we notice that there's a world file built. Right? Okay. Okay, so now, and the very last thing we're going to do is there are a bunch of parts. If I'm going to try to create a URDF file, there's a bunch of parts that are kind of just there. So we want to merge those parts together so that, and you get the collision type. I'm going to use convex hull, but I can use original message or bounding box here. Okay, and I can click on hide original parts after merge if I want. Merge links. This does take quite a while, so it's at 1%. Maybe I'll fast forward the video, but I want to talk about why we're doing this, because in a standard CAD model, you have every screw, you have every bolt. You sometimes have wiring, sometimes you have things that are really not important from a visualization perspective or even a physics perspective. And I say not important, that's not exactly true. The weights, the masses of all those things are always important. But what we're doing is saying, all right, if I have a plate and it's got 12 screws, nuts, and bolts in it, and now none of those things move, they're all fixed together, I'm going to create one basically mesh part out of all those 12 things. And instead of having this complicated thing with 100 or so parts, now I've simplified it down to just a few STL file meshes that represent the robot. You still get the mass, you still get all the physics that you need. I'm just compressing that down. The original parts still exist. There's nothing changed or removed about them, but now they're just part of a bigger picture. It's much better for performance, especially if you're going to use that in Gazebo or editors that don't have that, require that massive GPU and cannot ray trace all of these points. We simplify all that. We bring it down into something much more simple. The other thing that we want to do during this process is we want to start to build up control code. We have all the parts well defined. Why not just start to pull all the data that comes from the internet? I have another video about creating control code for a singular part. What we're doing is doing that for the entirety of the robot. So we build up a virtual environment in a couple of ways. We have a local virtual environment built up. We have a cloud virtual environment built up. And we also build up a Docker container. So all those three things. And you're going to ask why. One is because the Docker container can contain exactly the way your robot needs to function, what version of Ubuntu it's on, or whatever that you're using. And we can use that to test all of the code in one place. And it's not dependent on the environment that you're running this program on. I can run that and export as necessary any way that we need to. That's the beauty of a container. So here you see, as it's processing these things, there's what just went past was a reducer, motor reducer. It went in, and it's building this kind of corpus of information while merging and compressing parts that don't need to be, well defined and overly complicated. So we're going to the most simple URDF possible while retaining the shape. And that's another thing is when we go to test these things, because usually you create a URDF file and you simplified it so much that sometimes you actually simplify it down past points in which are important to the simulator. So an example would be, this is not a robot, this is just a stand here. If I were to simplify this down, I would probably get rid of these little, you can't see that, these little spacers, these little rods in here. I would probably do that because it would just make this thing much simpler. But the reality is, if this thing could move around, is a possibility that these little tiny pieces that are sticking out here could become collisions, and you won't see that if you've simplified the robot down to this very, very simple structure. You're going to lose some of those features. The other thing you're going to lose is the masses associated with it. And so when we talk about robot sim to real, that is one of the biggest issues, is that we've simplified the robot down in the URDF file so much so that we've lost some of the detail. And when we go back and we try to send commands to the real robot doesn't respond in the same manner as a simulated robot. So obviously that's something we take into concern in our robot control hub. We do a true up, the real robot versus the simulated robot. We go sim to real to sim to real, which is it seems complicated, but the reality is it's quite simple. There's a simulator. They were using Isaac Sim and Isaac Lab. And then we also export and run the same things in Majuco. Then we run it on the real robot, meaning that we get back the metrics, the real movement of the real robot, how precise it can be. Some robots have a lot of play in the joints, and it's not very stiff compared to what we saw in the simulator. So we do a true up. We say, like, this is what's happening in the simulator, this is happening on the real robot for the same movement, the same joint states that we want. The time it takes for the real robot to perform the action is different than in the simulator. We wish it would be the same. The reality, it's different. So, and these are the reasons why when you see robots kind of fail, especially robots that walk, it's because the real robot and the simulated robot are not the same. They're just vastly different. And if you send commands in nanoseconds to move a robot's legs, those commands will be interpreted differently in the simulator than they will in the real robot. So we have to do that true up. And that's why you see robots hanging from gantries, because the reality is we have to get that timing correct. And the way to do that in simulation is to get the real robot, stick it up on a gantry or a rig, and then perform those same actions, send the joints and timings and all of that, the actions back to the model, update the model with that. Otherwise, you're just kind of playing in simulator, and it's not going to directly transfer to the real robot. Okay, I was stalling a little bit, but we were about 66% done. I think I'm going to pause the video and bring it back to when we're at 100. Okay, let's continue. I've stalled a little bit just to make sure that everything worked as it was supposed to work. It merged all the parts. I'm going to click on OK. And now you can see there's visuals and collisions here, and joints, as it's supposed to be. And then finally, I can export to URDF. I can export the articulated USD file. I can export SDF, Majuco, even ROS control config. So these are the kinds of things that we would export. They would go into a folder intuitively inside of the app, but they also can be exported to wherever you want. So if you click on export, it goes in two places. So let's just, we actually want the URDF file, right? So let's export the URDF file. And so I'm going to put that on the desktop. I have one called Amber, but let's create another folder called Amber, and we'll call that 2, just for posterity. Create and open. So now it's going to go off and add all of these links, joints, meshes, everything to this assembly. And there it is, 156 STL files. Okay. So we have the STL files. We can take a look at them, and that's probably the last thing we'll do here. Let's go to the desktop, look at Amber 2. I also have a URDF visualization tool. This is the URDF. 100% complete. I think that's where we'll end it, and we'll thank you for taking a look here at the, I don't even know what we name this tool because it does so much. You can actually use the same tool to get articulations for a refrigerator if you wanted to. So I think in the next one, we'll do this a little bit further, and we'll show the visualization at the end. Thanks. Have a good one.